So last slide, our last lecture, we talked about the particle nature. And we're going to get into the particle nature a little bit more. So if some of that was a little confusing, it's all right. We're going to work on it, okay? But let's talk about that relationship. So I said that you had to have a minimum amount of energy and you had to have a minimum frequency. So let's talk about how that relates. So that is going to be our particle equation. So this is going to be our particle equation of our light. So E is going to be our energy, H is going to be Planck's constant, and V is our frequency, our nu. So E is energy. It's going to be the energy of our radiation, our light. And remember, this is going to be in joules because we measure energy in our joules. H is Planck's constant. So it's another constant that's going to be in the back of the book that's going to be given to you. And this is the value, 6.63 times 10 to the negative 34. And this is a joule times a second. Okay? And then V, our nu, is our frequency. And remember, frequency is 1 over a second. So if I multiply H times V, joules times a second, times 1 over a second, the seconds will cancel, and I have just a joule left. Okay, so this is my particle. But remember I said that light is both a particle and a wave. So I need to be able to put those two equations together. So we have the particle equation, E is equal to hv. So this relates my energy to my frequency. And we also had our wave equation. C is equal to lambda V. Now what if I want to be able to talk about my light from an overall standpoint? I don't want to just talk about the particle side of it or the wave side about it. I want to put the whole thing together. And so if I put the whole thing together, I can get this equation. E is equal to hc over lambda. E is my energy, still in joules. H is Planck's constant. C is my speed of light, same as here. And lambda is my wavelength in meters. How we get this combined light equation is from these two. Okay? So my similar unit is my V. So that's my similar unit. So what I want to do is I want to rearrange this equation to solve for V. So I'm going to divide both sides over by my lambda so that I get C over lambda is equal to V. So what I'm going to do is I'm going to take this whole thing that represents V and plug it into here so that I get E is equal to H, and then for V it was C over lambda. And that's how I get my combined light equation. So right now we have three equations. We have our particle, our wave, and our combined light equation. So depending on what problem you're doing and what was given to you, depends on which one you're going to use. So with that being said, let's look at a problem. So this problem says, calculate the energy in joules of a photon with a wavelength of 52 nanometers. And just for your knowledge, I tell you it's the ultraviolet region. So what am I looking for in this problem? I'm looking for the energy. Looking for energy in joules. So that's what I'm looking for in this problem. So then it says, well, what do I know? What did they tell me? They told me the wavelength. Wavelength is 52 nanometers, and you can say that's in the UV region. So I have wavelength, but I want energy. So I have wavelength and I want energy. So wavelength is kind of like the wave nature of my light, and energy is my particle nature. So I have the wave nature and I'm trying to get to the particle nature. So I need something that combines both aspects. And so since I need something that combines both aspects, that's when I want to use the combined equation. So here I'd say, okay, I want to use my combined equation because that has both the particle and the wave aspects. So now I gotta go, okay, well I'm looking for E, what is H? So remember H is Planck's constant, 6.63 times 10 to the negative 34. And then C is my speed of light, 3 times 10 to the 8th meters per second. And wavelength, But what are the units supposed to be? So remember, it always has to match my C. C's units is in meters there, so this has to be in meters. So I need to convert it. So 52 nanometers. Nanometers go on the bottom, meters go on top. Nano stands for 10 to the negative 9. Goes on top, opposite side of the prefix. So get 52 times 10 to the negative 9 meters. So now I can plug it all in. So when you're doing this, you want to always keep your scientific notation values in a parentheses. You want to use a lot of parentheses when you're doing your math here. Can't use too many, pretty much. Alright, so whenever I do this, I end up getting that the energy is equal to 3.825 times 10 to the negative 18. So let's look at units. So I have a second here. This is 1 over a second. They're both on the top, so that means they cancel. I have a meter here and a meter here. So a meter divided by a meter cancels. So the only thing I have left is a joule, which we know is what my energy should be in. Energy is in units of joules. So 3.825 times 10 to the negative 18. And you might say the same thing, how do I know that this is in the right range? So you could go all the way back and say, okay, so energy here, we just know low energy, high energy. And we said specifically that the energy for visible light was 10 to the negative 19. So if this is 10 to the negative 19 and ultraviolet to nearby, then I know that it's got to be some 10 to the negative number, but a little bit of a higher number, or more positive. So instead of 10 to the negative 19, we have 10 to the negative 18. So just a little bit bigger. Now, I want to actually show you a second way that you can do this problem, depending on what you think, what comes to your head. So this is going to be a second way for you to be able to work this exact same problem out. So let me just erase my screen here. Okay. So say you get to this point, and you say, okay, I've got wavelength, I've got energy, but you don't think about using the combined equation. You're like, I don't remember that, or it just didn't come to your head. And so you've got wavelength, and you're like, well, the only equation I know that has wavelength in it is my C is equal to lambda V. All right, so say that's all I know. So you're like, okay, well, I have lambda, C's a constant, so I don't know, maybe I need to do frequency. Okay, so let's just try that. Same thing here that we did before. I have to convert my nanometers to meters because it has to match the C. So C is 3 times 10 to the 8th meters per second. My wavelength is 52 times 10 to the negative 9 meters. Divide that over, and I get that my frequency is 5.7692 times 10 to the 15, and if this is a meter divided by a meter, they're going to cancel, so just 1 over a second. Alright, so we found our frequency now. And so you're like, well, that's not what I was trying to find. I have frequency, but I really need energy. Well, what's that other equation? Oh, that other equation had energy in it. Energy is equal to hV. And H was my Planck's constant, my 6.63 times 10 to the negative 34 joules times a second. So if I know H, and I already solved for V, I can find my energy. So plug in Planck's constant, plug in the V, and you get that your energy is 3.825 times 10 to the negative 18. The frequency is a 1 over a second. This is a second, so they cancel. So all I have left are joules. So if you notice, we get to the exact same answer. The difference here is the first part that we did, we used the combined equation directly. We realized that I had a particle, a wave nature, and I'm trying to get to a particle nature, so I just used the combined. The second part was not really sure, but you remembered some equations, and so you actually did the same process, but what you did is you said, okay, I have my wave nature, I'm going to put it in frequency, which is kind of like my bridge, and then I'm going to go and then use this guy. So you kind of broke it down. Instead of using the combined equation, you used the two individual equations and you just did it in 2 steps. Whichever one comes to your mind is fine. You'll get the exact same answer as long as you do the math right for both problems. So it doesn't really matter which one you do. All right, so this is the end of this kind of little baby section. The next part, we're going to start diving in a little bit more as to what happens to this particle nature of light. Which way is it going, when it's emitting and absorbing light, and where is it moving around? And so just to kind of summarize a little bit about the electromagnetic radiation, the things you need to know is you need to know that spectrum in terms of energy and frequency and wavelength. Just kind of understand how these relate. Energy and frequency, if energy goes up, frequency goes up. And then how does frequency and wavelength relate? And then how does energy and wavelength relate? So in essence, if you know our 3 equations, you know those guys. If you know this guy, and then that. So here, if my energy goes up, my frequency goes up. If my wavelength goes up, my energy goes down because they're inversely proportional. And then frequency and wavelength are related. So the shorter my wavelength, the higher my frequency. Okay? And then as far as the visible spectrum goes, you need to kind of know where it's at in the energy and the frequency, and then you need to know the exact wavelengths and how they correspond to Roy G. Biv. And so knowing that this is our 700 to 750 to about our 400-ish nanometer scale. Okay? So on the next lecture, we're going to start getting a little bit deeper into the particle nature of light with absorption and emission.